Okay, so hello everyone. So let us continue on. So last time on previous lecture we started the second part, the deduction of the formalism, right? We're trying to achieve our objective here, and we spent most of the previous lecture. Okay, so we realize, we talk about this, that it's probably inevitable that we cannot build our formalism just using phenomenological quantities. If you try to cobble something together made out of purely those probabilities we would get from experiments, that would be unwieldy, opaque, and not very useful kind of formalism. So it seems to be necessary to introduce some formal element. Okay, that's something ad hoc that we just add into our whole construction. And this is probably a standard that even classical theories, most likely, most of them have to do something like that. You have to introduce something from outside, let's say, some new formal elements. So we spent a lot of time discussing, doing a philosophical discussion. What are the rules for introducing such ad hoc elements? Because we don't want to be arbitrary. We have to have some standards for ourselves. What is okay, what is too much, and so we figure out some criteria, and we applied those criteria, and we made a decision, executive decision, that those functions Q that we introduced for parameterizing the interference experiments with multiple subsystems and with only one system, all this stuff, those functions dependent on B sequences, so two sequences, we decided that, okay, we can introduce those and use them as a basis for our future emerging formalism, okay? And then, okay, if we made this decision, we decided that this is okay thing to do. So we had to somehow like define those functions to work with them. And the simple approach, the stupid approach would be to just, okay, so we have a bunch of experiments. So I guess each of those experiments, we have those probability distributions, which are known values, and we can just use them to construct an infinite system of constraints for our Qs, okay? And this could be a definition. We know that we couldn't like solve this whole system of constraints, which are equation constraints, because if we could, then Qs would be phenomenological quantities. Okay, we know that this cannot be done. We also talked about it. The second hour was about that. So we know, so that would be just an infinite number of constraints, and every time we look at some Q, we would have to like check every one if it's not violating and stuff like that. And that would be just impractical. It would also violate our standards that we defined for ourselves. So that's no go. This approach will be no go. So what has to be done in that case, rather than those constraints, solving them and stuff like that, you could like try to figure out like a minimal set of properties that you force on those functions Q, and those so that those properties are sufficient for Qs to satisfy all the constraint. They are not sufficient and necessary, but sufficiency is enough. So we are risking, by doing things like this, we are, defining some structure for Qs if we pick our properties, intelligently, and we are risking that maybe we are, overdoing it a bit. Maybe a smaller or less fancy conditions would be enough to satisfy everything. And maybe we are just asking a little bit too much. But even if asking a little bit too much, we still will, fit to every experiment and stuff like that. And, so we have five properties here. And to be frank, I will go over them in a second. And to be frank, when we continue our journey, it's difficult to say it like to prove this, but I think you will see that we are not overdoing anything here. It seems that to fit every single requirement, every single experimental result that we can imagine, I think it would turn out that this set of properties is just right. This is it. Okay. Maybe there is no other choice actually. And the properties are so they are like, because those functions Q are kind of like the simplest way to generalize probabilities. So we have those multi-time probabilities from experiments that are probabilities on a space of sequences, of one sequence, okay? So like the simplest generalization of that would be to have a distribution, not necessarily probability distribution, but some distributions on pairs of sequences, right? We go from 1 to 2. That's kind of like the simplest thing you can do. And so if this is like the picture we have in our mind, what those Qs are doing, then we could like, okay, so probabilities have some, positive, normalized and stuff like that. How those properties could be generalized to this, more advanced case of complex value distributions on pairs rather than on single sequences. And those properties here are, you can kind of trace back them to this kind of reasoning. And so the first property, normalization, and take your Q, sum over all the arguments, is 1. So this is like straightforward generalization of normalization for probability distributions. Q2, causality. So it says that you have those two sequences, but non-zero, the distributions are non-zero only when those sequences meet at the end. This, of course, cannot be seen as a generalization of any property of single sequence functions. But this guy here, its main purpose is like when you combine it with other properties we have here, this is what's responsible for satisfying the first observation about causal structures. Okay, when you marginalize over the latest of those phenomenological probabilities, you get shorter one. So this guy here, that the sequences meet at the end, this is what's necessary to get that. We have third property. This is just a factorization rule we discovered at some point. Q4, positive semi-definiteness. So there are a lot of ways to write down this rule, and this is like I think the most universal. So this guy is. The other way you could put this is like if you take this Q, F plus, F minus, and treat F plus and F minus as indices, then you can think of Q as a matrix. Okay, that's indexed by a whole sequence. Okay, each sequence is just one value of an index, and then when you like look in this way on your Q, then this condition written down here is equivalent to saying that this matrix we just created is positive semi-definite, right? So this is, of course, where did we got this? Well, probabilities are positive. So those guys, the closest thing is positive semi-definiteness. And the fifth one is the most interesting. It's biconsistency, we call it. So you take your Q and you sum over, you pick timing, Tj, for example, and you sum over Fj plus and Fj minus independently, okay? And as a result, you get a shorter Q, all right? So this guy is particularly interesting. and we will shortly focus on it. So keep biconsistency in mind, and I'm just finishing comments on the properties. So now, once you start combining those properties together, so we did here like a rundown, what they give you and why we think they are sufficient to, you know, to the sufficient conditions to satisfy everything. And one of the things that you can get from biconsistency specifically, sorry for ugly handwriting, but since the diagonal part of Q, when you take F plus and F minus, the same is gives you the probability, right? You can use this to combine with consistency to actually calculate what is because we know from our observations that those quantum probabilities, they violate the consistency condition which all classical theories always satisfy, right? And we wrote it like, if the consistency was satisfied, then in this inscription here, you would have equals 0, right? Because the marginalized guy would be the same as the shorter probability, right? And we discovered that in quantum case, there is some reminder. There's something on the right-hand side. And now using biconsistency, we can actually calculate what this reminder is. And this reminder is you take this Q, you set all the arguments to be like a diagonal, except for the one you are marginalizing over. And here you sum over the off-diagonal parts only. So in a sense, in this quantum theory, it's non-classical in a sense that there is no trajectory picture because of interference, because of diagonal parts of Q. This is what quantifies interference for us. So this interference, this Q, is responsible for violating classical picture, essentially. That's why it's non-classical. But on the other hand, the consistency somehow survives, but in a newer, more expanded form, right? So let us focus on this now. So like I said, the consistency for probabilities was key in classical theories because it guarantees then that there exists this master distribution for whole trajectories, right? So those multi-time probabilities can be thought of as just sampling of some underlying trajectory, right? And the consistency is crucial for this to work. So if we go to quantum and we have this biconsistency, is there something analogous then? We don't have. So does this biconsistency imply that there exists this master Q that's a distribution, but not for one sequence, but for pair of sequences? Is there a bi-trajectory picture then? Okay. And as it turns out, the answer is positive, but there is a twist. We have to discuss this. And one more thing, the functions that satisfy those 5 properties are called in the literature bi-probability distributions. So now Qs are bi-probability distributions. And when I say in literature, I mean in the literature we wrote, okay? Because there is an alternative name for this similar functions. Historically, people use something similar, although there are crucial differences, and they call them decoherence functionals. But I think it should be, I don't like that name, and I think it should be outmoded. Bi-probability distribution is better than that, okay? So bi-probability distributions are Qs. So that was for what we did last time, okay? And now, so let's focus on this bi-trajectory picture, okay? So we have, so the essence of So going from multi-time distribution, multi-time probability in classical guys to this distribution for whole trajectories, you can think of it, I mean, like picturesquely. It's like essentially you're saying, okay, so I have like sampling of something, of some sequence on the discrete time grid. And you are asking, okay, so can I now take this grid and make it denser, 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 until this is so dense that it's essentially whole interval of time, okay? Does this limit exist? Because if if I'm sampling on some grid and I make this grid infinitely dense, then I'm essentially sampling whole trajectory. Okay, and does this so this poses like a mathematical question? Does this kind of limit make sense? Okay, and if it does make sense, this is what this is how you define essentially this master distribution on space of trajectories. So you can think of extension theorem as like so we take let's say some p on multi-time p or q or b probability, and you want to take like a limit where this Tn, which is a it's a discrete time grid of times, right? It's a grid, and you want to like take a limit when this just turns into interval. Sorry, interval have two arguments, not dots, not dots. Okay, and same here. Let's say Tn 1 Tn. And as you can imagine, this is very like a crazy kind of thing you are doing, because if you are making more, you're putting more times, you are adding more arguments to your function. So this is like a, it's kind of crazy procedure. You are really invasive here, right? So you can imagine that this is, it's very miraculous if this kind of thing actually works and gives you something sensible. And but as it turns out, this is not so crazy, because there are like two conditions that you have to impose on those multi-time probabilities or multi-time bi-probabilities. There are two conditions you have to impose to actually make this thing make sense. And the one condition is, so condition one, conditions. One is consistency. For probabilities, that would be standard consistency we talked about. For some, some version of biconsistency, triconsistency, uniconsistency, whatever, whatever the functions are you are dealing with, but you need this consistency, but which we have for Qs, okay? And the other one is something that's called uniform bound. And this condition is like, so you have to take your functions, for example, TPs, and you have to calculate their norm one. This is specifically norm one, which is defined by you take sum of absolute value of a function. Okay, so it's like, all right, this is definition of norm one. For probabilities, this is kind of trivial, because they are positive. Absolute value does nothing for them. So just for probabilities, this turns into normalization. Okay. Which is one. But for bi-probabilities, this is non-trivial because you take absolute value and the normalization is for just raw Q, which is a complex number, right? So the condition of boundedness of this uniform bound is that this norm can be estimated from above by a number independent of n, of number of arguments. Okay, so you have your Q's, and you want to make you want to go to the limit where you are making number of arguments and number of times more and more dense, right? And you need the bound that's independent of number of arguments you are taking, okay? And like I'm saying here, for probabilities, this is automatically satisfied always. So that's why in standard probability or theory, you actually don't talk about this second condition when you talk about stochastic processes, because it's automatically satisfied by definition. But here it comes in, and you have to prove that this actually works. And you might think, okay, sorry if this is kind of technical, but this is, I'm really proud from this work we did with guys where we proved the theorem, and I just indulge myself in talking about it a bit. So, but there is a point to this. There is physics in this. This is not pure math. So I'm very specific about norm one. You might think, why is that? And the answer is actually quite. It's quite reasonable because these are distributions. Probability distributions or by probability are also kind of distribution, right? So when you have distributions, what do you do with them? You're not really looking at them. You calculate some averages, right? Expectation values with distributions, right? So like the object of interest is usually some kind of, you take some function x and you do the average, which would you define. So you would, for by probabilities, for example, you take some function x, which is a function of two sequences, and you average it with your by probability. Okay, so that would be like a by average, if you will. And now, if you want to estimate how large is this average, for example, does it explode or something like this, right? You take absolute value because it's a number. So you have absolute value of a sum. So this can be sum of absolute values, right? X plus F minus times Q absolute value, F plus F minus. Then, okay, so this can be a standard thing you do. Okay, so I can just take, instead of bothering with this X, just take this maximal value it can ever take. Okay, just pick the some extreme case. And then it becomes, it's a constant, right? And you can put it outside of the sum. So this maximal value or a supremum for all the domain of the function is something that's called a supremum norm, which is denoted as infinity. So this is a maximal value it can ever take. And you are left with some plus minus of absolute value of Q, okay? And this is nothing else than the norm one of Q. So that's why we are focusing on Q1, because as a distribution, this is the figure of merit for it. okay? And now, give me 5 more minutes, please. This will, now the physics comes in, okay? Because as it turns out, to get this boundedness, and so if this bound exists, this means that there is a extension theorem works. The limit of going to, you know, the infinitely dense time grid, then work, only then it can work, okay? So in other words, this bound is necessary to have a, okay, imagine what would be a consequence if this didn't work, okay? Then it would mean that the time is somehow fundamentally discrete, okay? Because you couldn't go from discrete grid to full intervals, because then things would explode. So it would, if this was the case, then you would have to deal with a theory that's fundamentally has discrete time. And that would be a very, very big thing, right? Big conclusion, and very problematic one if you start thinking about it. Because okay, so what is this fundamental grid size then? Where is the limit? Is it like, what kind of laws of physics would emerge from that? We haven't seen any indication that such a thing would actually be, that there is like the smallest unit of time or something like that. And even if you agree that, okay, let's think about it, let's accept that there is a fundamental unit of time, Planck time or whatever, but it's still a grid, right? So it starts somewhere. You go, increase from by the unit, but where is the zero? Who decides that? What decides that? Do all systems agree at the 0 point? You would have to answer all of those questions, and I think there are no good answers for that. So in a sense, we want to have continuous time, in other words. Okay? So what I'm saying here is, like, to have continuous time, you have to have this bound. Okay? So it's like mathematical condition that has really, very pregnant in non-trivial consequences here. Okay, and what is very interesting is that from mathematical point of view, if you just take all those properties from Q1 to Q5 that we had, you cannot find this bound. You have to put in physics. You actually have to put in some observations we made, that those biprobabilities are actually quantum biprobabilities, and only then you can find this bound. And the particular observation that's key here is Zeno effect, actually. Okay, this bound is made out of Zeno effect, essentially. Okay, and how do you get it? It's kind of, there's a trick to that, and I'll just show the trick, and then I won't continue with calculations. But the trick is interesting. So if we define our time grid for a second as so we just pick some time and divide it by n. Sorry, tj. Point tj on the grid is just, so equidistant grid. Let's make it like this, and then you take your Q for this kind of grid. You look at this norm. So it is a sum plus minus n modulus square, modulus, sorry, not square, fn plus minus. But now I can, if I go into under the absolute value, now I can use biconsistency to add, more times in between, like to make the grid twice as dense, let's say, right? So I use biconsistency to make it Where is my cursor? Okay. So I have sum here, and I sum over, how to denote them? So let me tell those guys. What's the comment? Indian's joke. So let me write it like this. So let's say, so we put, we make it twice as dense. I'm like overloading notation a bit here. And I put in, all the missing bits. So here would be Fn, Fn plus, then let's say phi n plus, and we just alternate like that, okay? And same for the minus arguments. Okay, so I'm just putting, by consistency, I'm just putting more arguments. And some, yes, and some. But now, I can make it now. I can pull out the sum out of the absolute value. Okay, right? And then I have sum over all arguments of the absolute value of this denser guy. So in other words, what I'm getting is like T2n. All right? And I can continue. Okay? So in other words, if I continue this, I get this bound that I take limit where n goes to infinity of Q1, where, this is how I have my equidistant grid. But that's like, okay, so I'm like touching on the Zeno schema, right? Where you take a infinitely dense interventions in your measurements in your infinitely dense measurements, right? And then another thing, because Q is positive, it's positive semi-definite, plus diagonal values are probabilities. I can go even further, make the connection with Zeno effect even stronger, because I can go under the sum again, and now do Schwartz inequality for the absolute value, essentially. So n goes to infinity. I have sum n plus this, and then p, the n of n plus times p tn fn minus, but square root. Okay, so now we are really close to Zeno effect, because if you remember, for Zeno effect, you take p and you go with n to infinity, and that would give you frozen measurements, right? Here you won't get frozen measurements because you are taking square root of p. Okay, this is the trick. This is what unleashes everything. But still, it gives you the connection with the with Zeno effect, and in particular in this, because we learned from Zeno effect that there is a short time behavior, right? That the survival probability, as we called it then, it's like t plus delta t conditioned by some f ff was 1 minus v f t squared delta t squared. Okay. I'm almost done with this. If okay, So we had this V value, right? The short time behavior. And now we can actually invoke it here and obtain the final with some simple calculations. You can actually show that this V comes back, and the bound we are getting is the information about dimension, and you have x omega f, and you have integral of this v t dt. Okay, so this is the bound that you get, and it's finite, and it's independent of number of arguments. Okay, and it's explicitly depends on the short time behavior of dynamics of our quantum system. Okay, so if you want to see the all the nitty-gritty details of these calculations, check out the paper. There are references there to even more advanced paper with full proof of the theorem. So to tie this up, to get this extension theorem, that is to get a bi-trajectory picture, to get this master distribution on the space of pairs of trajectories, right? And in the process, obtain that time is actually continuous in your theories. There is no fundamentally discrete time in your theory, which would be really bad. To get this, yeah, it would be. I already thought about it, and it's like so many problems. I mean, we haven't seen any indications that something like this would. But if we want to have continuous time, the only way to have it is to actually have Zeno effect in your non-classical theory. So this is kind of crazy, I think. So Zeno effect is it's a peculiar thing, but it seems that this is the only way to actually achieve this continuous time, let's say. All right, so let me wrap up this weird mathematical formal discussion with a conclusion, and then we go to break. Okay. So, in other words, by taking all those 5 properties, especially the by consistency that we just took, and now we combine it with observation of Zeno effect essentially, so we can add next 6th property, right? Because this was all we needed to actually deduce to prove that this extension theorem works, that this continuous time limit actually exists. So this could be seen as a 6th property, okay, fundamental property, and let's call it by trajectory picture. And it's let me write it in full glory, because there is a certain asterisk here. The B probabilities Q F E N associated with a single observable F are discrete discrete time restrictions of a complex valued measure U F plus F minus F plus. So is a measure on the space of B trajectories. By B trajectories, I mean that we have a pair of functions that go from T pair of functions with values in so discrete values, continuous functions with discrete values. Okay, in the domain of the observable, in the spectrum of the observable. And restriction means that Q F Tn of Fn for sequences, specific sequence. So this is analogous statement to what we made for classical theories, but now you have to do double integrals. So you take your discrete time restrictions, which you can write as delta Fj plus F plus at time Tj. So this is a value of trajectory at time Tj of a plus component of B trajectory, and analogous for the minus component. And you have your integral with your Q, let's add QF, because it's associated with F, plus minus, and the differentials. Okay, makes sense? In particular, yeah, and you get Q. Double integral, I mean, it gives you this, Q, discrete time Q. It's very simple. And in particular, due to
F at point x0 is integral of f of x delta x minus x0. Just improve way of writing f at point x0.
Sorry, I'm not fully following yet because I'm distracted by writing. So due to the fact that the diagonal part of B probabilities is the measurable probability, right? When we use this with our newly acquired master measure, we get something very interesting. That P then PF, so our phenomenological probabilities equals, again, double integral on M, and you have your restrictions, but now you take your components of B trajectory and you just force them to intersect at those chosen points in time. Okay, and you have your Q, your master measure, F plus D, F minus. Okay, so this means that the probabilities we observe, they are always effect of some interference. right? Because you take your B trajectories and you force them to intersect at certain points, but in between those points, they just run like that. And you have all the contributions from off-diagonal parts of B probabilities, which means that there is interference in between. It's going on, and this is what produces you what you observe. This is the reason why there is no trajectory picture, no classical trajectory picture, because it's a B trajectory picture, essentially. Okay, and it also, coming back to Zinn effect, which is so fascinating for me, because traditional explanation for Zinn effect, I mean, that in a standard formulation of quantum mechanics is like, oh, you have Zinn effect because you are collapsing. You are frequently collapsing the states on some, some eigenstate of observable, right? And this is how everything is frozen, right? But this, and this explanation, of course, hinges on how real the collapse is, which we discussed in the very beginning, that this is like the most problematic thing in the standard formulation. And like assuming that is a real physical process is extremely problematic. And that's why you have measurement problem and all other interpretative problems with interpretations for quantum mechanics. But this gives you something else. This gives you a different explanation. Because, if what you observe is a effect of interference, and Zinn effect is obtained when you just, you squeeze those time points, right? But because your bi-probabilities, they have, positive semi-definite, they are normalized. So there is some, like conservation of, I mean, if you squeeze here, it just starts to spill out in between, right? And we can say this spillage here. This is what quantifies this spillage, right? Because the norm, when you make it, you squeeze this, the norm increases, which means that it's more and more there is more and more interference, okay? But you are squeezing it so much that you basically everything just like everything degrades to its like constituent parts once you reach a certain threshold, and then all of a sudden you get this universal behavior in a sense, right? For every quantum system, it will behave in this way. You expose this most fundamental like short time behavior in this way, and it's and you squeeze it, it goes so much into off diagonal, and it could either break, but it cannot break because we have to have this extension theorem working. So the interference becomes constructive or destructive. However you want to look at this, and as a result, it produces you Zinn effect, where everything is frozen from the point of view of measurer. So it's a Zinn effect is just extreme case of interference effect. Okay, no collapse needed to explain it.
In some by trajectory picture.
Yeah, which this is where we got so far.
It's not very intuitive, so it is not better explanation.
Well,
because these are not real trajectories, what you might think when you do the two-slit interference. There is not two-slit interference. Then the picture about this interference mixing with the by trajectories makes, I don't know if this is a good way to talk about it.
I mean, this is, I would say this is the most natural way to talk about it.
Okay, but typically, when we study quantum mechanics, when we talk about interference, we think about two-slit experiment, and this is just, and this is, I don't know if this,
well,
if this by trajectory is the by trajectory from two-slit experiment.
Well, when you talk about in standard, we went through that.
No.
We went through that. You essentially don't explain interference. You don't have.
No.
There is no.
But saying that this is better explanation because it is
Oh.
Picture.
No. It's more than that. It gives you a picture. It explains Zinn effect in the same way as.
The picture, what's this trajectory which interfere in the.
I have argument why it's actually objectively better explanation. Maybe not because one. No. One. It's the same. You use the same explanation as for any other interference. Okay, that's one. So that's efficient. But two, more important, you don't have to rely on collapse. Because if you have to rely on collapse, then you have to explain collapse to explain effect, and that's just, nobody did that so far. Probably because there is no collapse, most likely.
The way you are presenting it can mix in pairs of people like me who might think about some two-slit experiment where you have only one measurement at the end. There is no this trajectory in the sense you are talking, even not by trajectory. Even not by trajectory.
We spent like 2 lectures explaining how slit experiments are actually sequential measurement experiments where it's very natural to think. So if you adopt this point of view, which I think is superior, because, well, we went over that, right? Then this is like the, okay, yeah, but like you were saying, a matter of getting used to it. But
that's why what you say is not what somebody is using. This is not very objective statement.
No.
Explanation.
I would say that it's worth getting used to it, because then you don't rely on collapse. Okay, that's why I would say this is why it's. Then you are wrong. You can be wrong. I mean, it's not illegal to be wrong, but
I might have my faults, but I am never wrong.
Well, I am a liar, right? That's a paradox. Okay, so one more thing to finish this up. However you feel about intuitiveness of this, for me it's very intuitive. For everyone else, I'm sure it's not very intuitive. But there is value in thinking in bit trajectory picture. Okay, so one, but there is a caveat here. Okay, because at this point we can show this bit trajectory picture, but only when there is one observable. Okay, all the proof I sketched for you, this works when you have a sequences when there is only one measuring device that measures the one observable f. Okay, if you start mixing different observables, the arguments I just showed you, they don't apply. You have to do something else. So it would be very tempting to say that since we observable stuff we describe by probabilities, and by probabilities are simply restrictions of this master by probability, this master measure. So this master guy is like the master object of our theory. Everything in formalism is spawned. This is a source for everything in our formalism, but it's not really the case, because this guy that we found out at this point, at the very beginning, is only associated with single observable. We have to, so the intuition would be, and this is where we get in the end, that there is even higher, there is a guy higher in this hierarchy. The true master object will be a by probability distribution, but that's not tied to any specific observable. Okay, but to get there, we have to. I don't think we can show it at this point. At least I don't know how. We have to go build some more stuff, and only then we will have all the tools to actually show that this is the case. But this by trajectory distributions, this is where we are looking for a master object of our theory. Okay. of our formulation, of this formulation. Yeah, so let's take a 5 minutes break. All right, so let us carry on. So with this B trajectory picture, at least a hint of B trajectory picture, you know, we are, of course, we are not done yet, because at this point, you know, there is a crucial thing. There's one more crucial thing that every good theory should have. Okay, so right now we have like okay, those by probabilities, maybe those master by probabilities are like the things that describe a system, describe dynamics. You can derive observable stuff from those distributions. That's cool. That's very fine. Okay, but at this point, we cannot like, maybe, although it's not really possible, but maybe we could try to like tabularize some by probability distributions for different systems and make an atlas of different by probabilities, and then we would have the description of every species of system that we can encounter. Essentially, do something that biologists do. Okay. But even this we couldn't do because by probabilities are not. This is how you do biology, right? Or chemistry. You have a great book of recipes, great atlas of facts. But even that wouldn't really work. Even that wouldn't work because by probabilities are not phenomenological objects. You cannot like access them through some measurement, direct or otherwise. And especially you cannot do this for those master distributions. Those are like logically inferred from by probabilities things. So what we are really missing here, we need this ability to actually construct by probabilities from some understandable, simple building blocks. The way, if we can figure out this, this pattern, how you construct them, then this is what essentially laws of physics are. Have some simple things and have some rules how those things should be combined to give you something that describes your systems, right? And if we have access to something like this, then not only we could like, describe things we saw, but we could also postulate some systems that maybe no one have seen yet. But in principle, if we identify those laws and those building blocks correctly, then whatever we create according to those laws, even if no one seen it yet, in principle, it could be observed. There is some piece of a universe or something can be built that will create conditions where our postulated thing would exist and would be then described by probabilities we just constructed from our fundamental laws. So now we go to we want to identify those guys. Okay, we want to essentially open up by probabilities, which at this point are just some functions with some properties, but want to open them up and see what's inside, what makes them tick, and find the building blocks which we can like look at them and understand how to use them and how to combine them to build new by probabilities or explain those that we already have, right? In other words, we are going to something with next section, number 6, the Hilbert space representation. Hilbert space. Right, so that for all us experienced quantum mechanists, right? We are not surprised that we are, there some structures on Hilbert spaces should appear sooner or later when you're talking about quantum mechanics, and this is what we want to actually identify in this whole our story. So the first step is to actually we need to find a way in. We have those complex value distributions, right? And we need some we need to find the reason why to connect them with Hilbert spaces actually, because so far there is maybe we don't see any explicit indication yet that we should even bother with Hilbert spaces. Some vector space with over complex numbers with inner product, right? This is what Hilbert space is. How to stick your toe into the door, foot in the door to actually get to this point where we have a reason, a justifiable reason to actually pursue Hilbert space representations. And there is a very interesting mathematical observation that we will rely on to actually get our foot into the door. So first step is 6.1 by probability distributions as inner products. So look, there is a theorem. There is a guy called S. Gooder. He wrote some papers, interesting papers, although I learned from colleagues, mathematicians from university that they weren't surprised that someone went there where the Gooder went. So for me, it was like, ooh, how insightful. But they said, oh, this is a standard thing you do, actually, when you see something like by probability. So this is like an immediate thing. But so the theorem from Gooder is, he's basically saying that, okay, so you have a positive semi-definite function of two arguments. It's complex value, that's okay, but it's normalized positive semi-definite. Oh, so such a thing is it has to, it's always possible to represent something like that as an inner product in some Hilbert space. This is what the theorem essentially says. And my colleagues, mathematicians from university say that this is a super standard thing you do. But the construction itself, to show that this is actually possible, it's for me, it was surprising, eye-opening. And I want to go over it with you, make some steps to actually show what I mean by that. That there is this inner product representation by probabilities. So let's take one of our by probabilities. It has some sequence of observables. Let us also associate it with some initial condition. So this initial condition, if you remember, the diagonal part of this Q is some probability distribution. And when we talk about problem of initialization, so we wrote something like this, and this P is, right, you remember it is like, because initialization is like a measurement with a fine-grained observable device, right? And so the initial condition is set by some result of such a measurement, and you can add like some uncertainty in preparation of this initialization. So this probability P tells you that, you know, you have the initialization was done with this probability with device K, and the obtaining result small k, and you have, you know, whole distribution over all, you know, different devices, different results. This is what we, yeah, we already did. I mean, this is what they will amount to. Okay, so we take our dude here, our by probability, and now let's couple steps. One, let's take an orthonormal basis in a C omega Fn vector space. Okay, so we just take standard vector space. It has as many dimensions as there are different sequences. Right, this is what it means. This omega, for every sequence there is one, you know, one value of index, and we take some orthonormal basis. So we take some vectors psi. Let's keep all the indices in full view explicitly, because we, you know, maybe everything would depend on those choices. And they are indexed. The elements of basis are indexed by whole sequences, right? This is sequence as an index. So Fn belongs to omega n, just to say it's an n tuple. And the orthonormal basis, so in this vector space, you can have a standard inner product. So by orthonormal basis, I mean they are orthonormal with respect to this standard inner product. So you take this guy, you take this thing, the n 0, some n minus, let's say. And this orthonormal means that this is just delta from 1 to n. So every component has to be the same. No, it's not modulus. It's a condition. So you have basis. So it's a set of vectors. So, sorry. Set of vectors sitting in this space, okay, such that sometimes you write semicolon, okay, such that the indices, right, we have indices in short perpendicular Kreska.
The first.
A vector, not vector. Bracket notation for vectors.
Yeah, but can be also absolute value. And then why this absolute value is lower? Okay, very dense notation. To say that this is a set.
A basis.
Such vectors that the inner product is the
orthonormal basis, in other words. This is sophisticated for you, Mariusz. I think
you already got something. F at x0 is equal to integral.
Mariusz, I think you have to brush up on your basic maths, you know, because this is complicated for you. I mean, man.
Something with thousands of symbols that you said set of orthogonal vectors. This picture set.
All right. So now we have our vector space with bases, so we can have some. You can take a vector alpha. So some coefficients. Vector span by on our basis, right? No, decompose into, how do you say it? When you have vector and you decompose it into bases. Okay? And these are some complex valued coefficients. Simple? And you have some vector beta with some coefficients b on the same basis. Psi. Zero. We are dragging all those indices along because we don't know which one will be needed in the end. Okay, so we're dragging them along, and now we have those two vectors, and now we can define a function, which I will very let's say. I anticipate what this function will do, but it's a function of two vectors, alpha, beta. Let's keep all the indices because who knows what will be necessary to keep track of. And this function works that you take here a sum over two sets of sequences, A, F, so coefficients from vector alpha, okay? Here you put our Q that we selected in the very beginning. And coefficients B. So here's plus. Okay, we take this kind of function. And this thing here, this kind of function, is actually a proper, nice inner product. So we have standard inner product, just bracket, but we can define some,
Standard inner product, I would have a star.
Very nice, thank you. I actually want star to be here, which I can do, right? And this is a inner product, actually. This is an inner product, and Q, by probability, plays here a role of a metric, right? And because this Q is positive semi-definite and has all the other properties we listed for them, this is what actually gives us this function double bracket. This is, thanks to all those properties, this is actually, this is proper inner product. So we can now take our vector space that we started with, right? And combine it. So we take our vector space, combine it with this inner product that we just defined, and this is Hilbert space. This Hilbert space is a vector space plus inner product. So this is Hilbert space. Exactly. Or in other words, you can Q is an inner product because yes, it's yeah. This is how because actually you can extract Q from this whole stuff, the function that we started with, right? By taking an inner product between the basis elements. It's actually, if A and B, coefficients A and B are just, deltas, we're just looking at our basis vectors. This is actually That's why I dragged all the, all the things with me, because I don't know which one will actually be important here. So plus psi t, yeah, 0, and minus. Okay. So my colleague, and also we keep indices everywhere. I mean, because we just want to be super careful here. We will start to eliminate them in a moment. But first so this is like this is the way in. And my colleagues mathematicians say, you see a function of two arguments that is positive semi-definite. There is always this kind of inner product. There's always connection with Hilbert spaces immediately for any they biform or however they call it, dual. I don't know this math jargon, but there is this is like a standard thing. So this is why it's natural to connect by probabilities with Hilbert space structures. And what? So one more useful thing that we can do here is to maybe be a little bit more. So, by Mariusz, we'll be finishing soon, unfortunately. Okay, so one more useful thing to do here is I just said to you, just said in words that Q plays here the role of metric for our inner product, right? Standard inner product has a simple metric that's identity. So in other words, metric is some kind of matrix from the point of view of this whole Hilbert space. So we can I want to introduce this matrix that's connected with our Q. Okay, because we will be using this later. So metric. So metric is simply so like I said, no, not like I said, but metric. So we have this fancy invented induced inner product, right? But you can also rewrite inner product, rewrite it in using the standard inner product that we started with in the very beginning. But then so then you have to take brackets, but you have to put in the matrix that represents the metric of your fancy inner product, right? So just take and again, this is we'll soon define what it is, and we keep all the indices in beta, okay? And this equality actually gives us, so from this we can deduce what this Q with hat is, because we can evaluate this inner product on the basis elements, and this will expose, gives our explicit matrix elements of this Q. And of course, when you do this Q hat is nothing else than, so it's a matrix, and we take a element indexed by a sequence F plus and F minus, and this is just by probability we started, okay? So what? So in this sense, by probability is a metric. And well, there are some additional mathematical consideration you actually have to do to show this, that everything works as it has to be, but we just don't bother with it, okay? If you want all the sloppy details, just go to the paper. We will all we needed from this is our way into Hilbert spaces. We got that, we are happy. Now we can do something with this. And the thing we will start with, it's really serious business. It's really serious business. Everything before was it was playing. Now it's real. Measurement projector. Projector link. No, link. So, standard quantum mechanics, and we kind of touched on it in the very beginning that, measurements are essentially axiomatically connected to projection operators in some Hilbert space, right? This is like the thing that usually it's just postulated that this is the case. And now we want to use our powers to actually deduce this link from what we have so far. And this inner product representation is a key to doing that, but it's key, but we have to get everything we got so far, the observations and stuff like that. It's everything will play some role here. Okay. And there is so there's here some tricks, some mathematical tricks, and actually a pretty good bit of like consideration, philosophical nature actually, that goes into it. So let's break this down into steps again. At least I will. Yeah, let's do as much as we can. So let's start with a n equal 1 by probability. Okay, the inner product representation works for any n, right? You have some of the things we talked previously works for everything, but in particular, it also works for n equals 1, for single time by probability, which actually, due to causality, is actually the same as the single time probability, because diagonal part of Q is a probability, but when you have only one argument, the sequences have to meet at the end. So there is only one argument, so they are the same. So the only diagonal part is non-zero. So we have P of some F. No, not F. Let's take fine-grained K with some initial condition T1, T0, K, K1, which equals Q, K, P, T1, T0, K1, K1. Okay. And now we can deploy here our construction from before. Next step. So we take our QKP because it's still by probability. So things we talked about previously work for it as well. So this guy would be okay. So basis T1, T0. We're keeping all the elements, metric K, P, T1, T0, psi K, P, T1, T0, K1. Okay. This is the formula. Right, this is it. And this metric, just as a reminder, it's semi-positive, and I should have said it here. So this Q guy, okay, it's semi-positive definite, but it also has its trace. It's always one. Sorry about that. I forgot to say it, because the trace of this matrix is nothing else than sum over F Q F F. So diagonal part of Q, you sum it over. This is probability, which is one. Okay. So trace is a diagonal normalization of the diagonal part. So trace equals one. But this I can rewrite as a trace over, let's call it Hilbert space A K. I can use trace formula here for convenience. And what is this HK? So this is a Hilbert space. So Hilbert space on the on our chosen Hilbert space that is made out of our chosen vector space, but with inner product, with standard inner product. Okay. We should, if we used this our fancy double bracket inner product, that would be formally different Hilbert space, but we will stick to this one because thanks to the invention of this matrix Q, we can carry the fancy inner product with us in the form of this metric matrix. So it's enough to just stick to the standard inner product for all the calculations we'll be doing. Okay, so that's so this is our formula, and on its own, it's nothing special happens. We just repeated what we did for the simplest case. But now we can. Okay, so we did this for K, but from our phenomenological considerations, we know that okay, we have this system. We measured observable K, but we can also measure coarse-grained version of K. Right? So we can also take we can take P K coarse-grained with the same initial conditions, same time, same serialization, some K1. And this corresponds. I mean, both are positive trace one operators. I mean, look, our conclusion will be that this metric is a density matrix, but steps are required to get there. But this is the density matrix is a positive trace one operator. Q is also a positive trace one operator. K1, right? And we can do the same, the same tricks as here. Convert it into trace formula, but there is there is a wrinkle here because we are working in different Hilbert space formally. We get bases. Get P. Let me explain why this is. I mean, for one, we are doing this construction independently of the previous one, right? So there is like no logical reason to actually have different Hilbert spaces, have the same Hilbert space in both cases. But two more important reason, if K bar is coarse grain version of K, there is smaller number of values, right, that the measurement can yield. This means that this Hilbert space dimension of HK bar is smaller, right? HK bar is less or equal to D. Okay. So we did our construction. Again, we have different Hilbert space, but we also have phenomenology. We have the law that when you do coarse grain measurement, only single measurement, right? You get the probability equals sum of probabilities of fine grain measurements, right? So this is what Pheno tells us, that P, K, P, T1, T0, K1 bar equals sum over K1 in a resolution, PK. Okay, we have to end soon, and this is not the worst place to end. Which, if we translate it to our Hilbert space representations, right? We get that trace over the coarse-grained guy with psi, K bar, T1, and all the other stuff. And the indices, fill it in for yourself. K bar, P, T1, T0. Another page. That this guy equals trace over fine-grained sum K1 over omega and the basis elements of in fine-grained T0, K1, and so on. And the metric indices, not fine-grained indices. This is what phenomenology tells us. And now the philosophy would come in, because you look at this, you are ostensibly describing measurements done on the same system, or the same observable, but do different graining, right? And you get representations that live in different Hilbert spaces. That's kind of wasteful, okay? So you can make a choice here to maybe make our description more elegant, and rather than multiplying entities for every observable, there will be different Hilbert space and so on, different metric, different all this stuff. We can make here an executive decision to actually, if we are describing the same system, let's put everything into one larger Hilbert space, okay? So we want to put those projectors and metric that live in this smaller coarse-grained guy, and want to extend it to this larger Hilbert space, larger Hilbert space for fine-grained guys. And this poses, if we want to do this, we have a problem to solve, because, you know, this extension there are infinitely many ways to do it. We have to pick something that's sensible and appealing to us. Okay, and this is a choice. This is a fork in the road. Depending on what we choose here, the consequences will carry on forward, right? And which choice we will do, we run out of time. This will be a cliffhanger for the next week. Okay, but a little bit of spoilers. The choice will be quite sensible. We would like say, okay, so projectors. Let's do it like that. That we take projectors and just map them on projectors, metric on metric, which is a choice. You could do, you could do it differently, but let's like keep the roles the same on both sides. And when we make this choice, we will, this will lead us to the like reasons to actually curtail the indices at some point. This will define the roles of those metric and these projectors more, to make more transparent what the roles of those operators. But let's leave this discussion for next week.